Here are solutions to homework set number 12 for ECE 376. This homework looks at filters, how to design filters in the Z-plane. One approach is to take a filter in the S-plane and convert it to the Z-plane. That's my personal preference because I'm kind of familiar with the S-plane. Z-plane I still think is kind of weird. One way to do it. The conversion from the S-plane to the Z-plane is Z is e to the st. So if I have 3 poles in the S-plane, I've got 3 poles in the Z-plane. The conversion is e to the st. For example, if I have this filter in the S-plane, I've got poles at -3, -7, -10. In the Z-plane, converting is e to the st. The poles belong at 0.97, 0.93, 0.90. And note you have to know the sampling rate. Change the sampling rate, I change the filter. So 3 poles in the S-plane, 3 poles in the Z-plane. I've got a gain to play with. Typically you pick that gain to match the overall gain at some place like DC. So if I do that, the DC gain of the plant is 2.38. Pick K so that the DC gain is also 2.38. In the S-plane, DC is at s equals 0. In the Z-plane, again, everything's e to the st. If s is 0, z is 1. So that's DC in the Z-plane. Pick K so the DC gain is 2.38. UZK is 0.00045. That's pretty common to have these small changes, or small numbers. There's my filter in the Z-plane. What the number 0.0004 means is that in one sample, the output changes only by 0.0004. Not a lot, but over a bunch of samples, a bunch of 10 milliseconds, it will change. Optionally, with this filter, I've got 3 poles, no zeros, so this actually has a delay of 3. Sometimes they'll add a z cubed in the numerator, so this filter just doesn't have that delay in it. A delay doesn't affect gain, so either one's valid. If we want to check, are these two filters the same? One way is to see, do they have the same frequency response? In the S-plane, I can have S omega go from 0 to 50 radians per second. S is j omega. G of S is basically the way you type it in MATLAB. In the Z-plane, T is 0.01, Z is e to the st. There's your filter in the Z-plane. Plot the gain versus frequency for G of S in blue, gain versus frequency for G of Z in red, and what you get is the same curve. This actually has 2 curves, the red and blue, on top of each other. They're so close you can't tell the difference. Same gain versus frequency means same filter. So this filter is the same as that filter, just different ways of representing it. That's for real poles. Also works for complex poles. If I have this filter in the S-plane, kind of what that one looks like, it's a bandpass filter. Gain versus frequency kind of looks like this. I can convert to the Z-plane using the same procedure. I've got a 0 at s equals 0. In the Z-plane, I've got a 0 at +1. In the S-plane, I've got poles at -5 plus minus j20. In the Z-plane, I've got poles at 0.54 plus minus j0.84. So, the form of the filter in the Z-plane, I've got 1, 0, 2 poles S-plane, 1, 0, 2 poles Z-plane. K matches the gain somewhere. I can't pick DC because I get 0 equals 0. Pick somewhere other than DC. I'm going to choose 20 radians per second. At 20 radians per second, the gain is 0.99 for G of S. Pick K so that the discrete time filter also has a gain of 0.99 at 20 radians per second. So S equals J20, Z is e to the st, or e to the j0.2. Gain's off. Pick K to make the gain match up. K is 0.09. So there's my filter in the Z-plane. To check, I can plot the gain versus frequency. In the S-plane, here's omega, S is j omega, G of S. In the Z-plane, T is 0.01, Z is e to the st. There's my filter. Plot G of S in blue, G of Z in red, and what you get is the same filter. I've got the two so close to each other, it's really hard to tell the difference. Same gain versus frequency means same filter. So again, that kind of says that these two filters are equivalent, just different ways of expressing them. The reason we like implementing filters in the Z-plane is it's really easy writing code. In the S-plane, I'd have to write programs that implement differential equations. That's not easy. In the z-plane, I implement difference equations. That's really easy to do. It's almost trivial. To see how that's done, take your filter in the z-plane, multiply it all out, cross-multiply. Note that z means the next value, so there's the next value of y, or 2 samples in the future, 1 sample in the future, y of k, and so on. This filter I have a hard time implementing since it uses future values, so do a time shift. Shift everything by 2, solve for y of k, and that's your program. At every sample, every 10 milliseconds, I've got to remember the current input, the previous input 2 samples ago, that's this guy. I need to remember the previous output, the output 2 samples ago. Then y of k is just that equation. Output the number, set the sampling rate, repeat. That's my filter. This is really easy to program versus in the S-plane, I'd have to be implementing differential equations. So that's the real reason for using z-transforms. If you're doing this in software, I should really be using z-transforms and a difference equation. This is actually kind of trivial, very easy to implement. But to analyze this filter, I need to be using z-transforms. The last one is kind of a cute one. There's a thing called an FIR filter. I can implement a filter using a tap delay line. I use the current value, previous value, 2 samples ago, 3 samples ago. That's called an FIR filter. With that, I can do some pretty amazing things. For example, come up with a filter to implement this filter, or come up with a filter to implement this gain versus frequency. Not really easy to do with capacitors, inductors, active low-pass filters. Pretty easy to do with a FIR filter. For an FIR filter, the impulse response of a ideal low-pass filter is just sine of t over t. If the corner is at 6 radians per second, it's sine of 6t over t. Amplitude of 0.2 gives me this, plus a second filter that has an amplitude of 0.4 at 4 radians per second, plus a third filter has an amplitude of 0.4 at 2 radians per second. Add these all up, I get that stair step. Plot the impulse response versus time from minus 20 to plus 20 seconds, and this is what I get. Again, kind of ugly, but these two are the same. If I have this gain versus frequency, I have this impulse response, because time and frequency are related. You'll be covering that when you take signals and systems. But given the impulse response, I know the frequency response. Given the frequency response, I know the impulse response. This is what it's got to look like. The challenge then is implement this in software. So what I'm going to do is, this goes out to infinity. That's a problem. I'm going to truncate it at 5. That's kind of arbitrary. That's just where I truncated it. So ignore this part, ignore that part. Implement this with 100 data points. So if I do that, here's time goes from minus 5 to plus 5 seconds with 100 data points. I'm going to shift it by 10 to the minus 9 so I don't get the 0 over 0 problem. Here's my impulse response. The DC gain is the sum of the data. This is off by a scalar, so scale it so that the DC gain is 1. And here's your impulse response. Total area is 1. Now implement that filter. What I'm going to do is take the input and remember the last 100 values. This is the weighting. I'm going to sit there and apply these weightings to it, add them all up. When I do that, I wind up with this impulse response, meaning this gain versus frequency. To check my answer, I can find the frequency response of this filter. To do that, I just sum up 1 over z to the n. Again, z is e to the st. 1 over z to the n, or in this case I, is 1 over z to the I times my weighting in my filter, my impulse response, this guy right here. Add them all up, and that's my gain versus frequency. Plotting it, I should have the stair step, and it's not too bad. It's a little bit off, but it's off because I truncated between -5 and +5 seconds. I only used 100 data points, and it's still a pretty good approximation of it. Adding more points would make it better. Adding a higher sampling would make it better, but also harder to implement. So that is filters in the z-plane, homework set number 12.